A B tree is a balanced multi-way search tree designed for storage systems that read/write large blocks of data like disks. Think of it as a filing cabinet where each drawer node can hold many folders' keys and points to other drawers' child pointers. The order, often denoted B, tells us the maximum number of children a node may have. Formally, a B tree of order B satisfies. Every internal node has at most B children and at least the ceiling of B over 2 children, except the root, which may have fewer. The keys inside a node are kept sorted, just like the labels on folders in a drawer. The height of a B tree grows very slowly with the number of stored keys n, because each level can branch up to B ways. The worst-case height h satisfies. B to the h minus 1 power times ceiling of B over 2 is less than or equal to n, which is less than B to the h power. Solving for h gives the well-known bound. H is less than or equal to ceiling of log base B of n. In other words, if you double the number of keys, the height increases by at most 1 level when B is large. This is why B trees are called logarithmic in the branching factor B, not in the binary base 2. The node capacity, maximum keys per node, is B-1 because a node with k children stores k-1 keys separating the child subranges. If a node is only half full, it holds at least ceiling of B over 2-1 keys. These formulas let you quickly compute how many keys a tree of height h can store, which is useful for proving space guarantees. A B tree maintains 3 core invariants that keep it balanced and searchable. Key range per node. In any internal node with keys k1 less than k2 less than k sub t and children c0, c1, ct, every key stored in subtree ci lies in the interval from ki to ki plus 1 with k0 equals negative infinity and k sub t plus 1 equals positive infinity. This is like placing dividers on a shelf so that every book in a section belongs to that section. Uniform leaf depth. All leaf nodes appear at the same depth from the root. This guarantees that any search traverses exactly the same number of nodes, ensuring predictable input-output cost. Sorted order inside each node. Keys inside a node are kept in ascending order. This lets us perform a binary or linear scan inside the node to decide which child pointer to follow, just like looking at an alphabetical index on a page. To search for a KK in a B tree, start at the root. Inside the current node, scan the sorted key array, often with binary search, to find the smallest index I such that k less than or equal to ki. If k equals ki, we have found the key and stop. If k not equal to ki, follow the child pointer ci-1 or c0. If I equals 0 to the next lower level. Repeat steps 2 and 3 until you either find the key or reach a leaf. If you reach a leaf without finding the key is not present. Because each node can have up to B children, the number of children examined per level is at most B, and the height is at most ceiling of log base B of n. Big O of height equals big O of log base B of n. If the node fits in memory, the internal scan costs big O of log B with binary search, but the dominant term remains the height. This explains why B trees are optimal for databases. Each level corresponds to one I/O operation, and the number of I/Os grows only logarithmically with the data size. Explanation: insertion adds a new key while preserving the 3 invariants. Step 1. Search for the correct leaf where the key belongs, using the algorithm above. Step 2. Insert the key into that leaf sorted array. If the leaf now holds at most B-1 keys, we are done. Step 3. Overflow case. If the leaf now has B keys, 1 more than allowed, we must split. Choose the middle key, which is the ceiling of B divided by 2, as the separator. Create a new sibling node containing the keys greater than the separator. Keep the lower half keys in the original node. Push the separator up to the parent node as a new key and add a pointer to the new sibling. Step 4. Propagate. If the parent now exceeds its capacity, repeat the split step upward. This may reach the root. If the root overflows, we split it and create a new root with 2 children, thereby increasing the tree height by 1. The split operation is analogous to splitting a crowded bookshelf into 2 shelves and putting a new label on the wall, the parent, to indicate where each shelf belongs. All splits keep each node at least half full, so the minimum occupancy invariant is never violated. Explanation: deletion is more intricate because removing a key can cause a node to fall below the minimum number of keys ceiling b over 2 minus 1. The procedure: Step 1. Search for the key. If it lives in an internal node, replace it with its in-order predecessor, largest key in the left subtree, or its successor, smallest key in the right subtree. This key is guaranteed to be in a leaf. Step 2. Delete the key from the leaf. Step 3. Underflow check. If the leaf still has at least ceiling b over 2 minus 1 keys, we are finished. Step 4. Borrow or redistribute. If the leaf has too few keys, look at its immediate sibling on the left or right. If the sibling has more than the minimum, move a key from the sibling into the deficient node and adjust the separating key in the parent. This is like borrowing a book from the neighboring shelf while moving the divider label. Step 5. Merge. If both siblings are at the minimum, merge the deficient node with one sibling and pull down the separating key from the parent, forming a single node with up to 2 times ceiling b over 2 minus 1 keys. The parent loses a key. If the parent now underflows, the fix-up recurses upward. Step 6. Root special case. If the root ends up with a single child after a merge, the child becomes the new root and the tree height shrinks by 1. Both borrowing and merging preserve the sorted order and the uniform leaf depth, ensuring the B-tree invariants hold after deletion. The minimum occupancy guarantee says that every node except possibly the root contains at least ceiling b over 2 minus 1 keys. To prove the worst-case space utilization, consider the tree when every node is exactly half full. A leaf stores at least ceiling b over 2 minus 1 keys. An internal node stores at least ceiling b over 2 minus 1 keys, and has at least ceiling b over 2 children. If the tree has height h, the minimum number of keys n-min it can hold is n-min equals 1 plus ceiling b over 2 minus 1 times ceiling b over 2 to the power h minus 1. A more compact bound is n-min greater than or equal to ceiling b over 2 to the power h minus 1. The maximum number of keys n-max is when every node is full. N-max equals b to the power h minus 1. Thus, the space utilization ratio of stored keys to maximum capacity in the worst case is util equals n-min divided by n-max greater than or equal to ceiling b over 2 to the power h minus 1 divided by b to the power h minus 1, approximately 1/2 for large h. So a B tree never uses less than about 50% of the possible slots, which is why it is called dense compared to a binary tree where many nodes may be empty. The proof relies on the invariant that after every insertion or deletion, nodes are kept at least half full, guaranteeing the bound holds for any sequence of operations. Branching factor, up to B children per node, often 100 to 1000 in databases for B tree, exactly 2 children per node for BST. Up to B children, but all data is stored only in leaves for B plus tree. Height big O of log base B of n very shallow for B tree, big O of n worst case big O of log n average for BST. Same as B tree, big O of log base B of n for B plus tree. Node layout, keys plus child pointers together for B tree, 1 key plus 2 pointers per node for BST. Internal nodes hold only separator keys, leaf nodes hold full records and are linked as a list for B plus tree. Search cost, 1 disk read per level, few levels for B tree, potentially many reads, deep tree for BST. Same as B tree, plus sequential range scans are cheap because leaves are linked for B plus tree. Range query, walk down to start key then follow child pointers, still big O of log base B of n plus output for B tree. May need to traverse many nodes, not cache friendly for BST. Very efficient, start at leftmost leaf then follow leaf links, big O of log base B of n plus output for B plus tree. Insertion and deletion may cause splits and merges that propagate upward but height changes rarely for B tree. May cause rebalancing, for example a VL red-black or become unbalanced for BST. Same split and merge logic as B tree, but all modifications affect only leaves, internal nodes only store separators for B plus tree. Typical use, database indexes, file systems, external memory for B tree. In-memory sorted containers, simple algorithms for BST. Database indexes that need fast range scans, for example MySQL in NoDB for B plus tree. Exam focus. Recall that B tree height depends on B, not on 2. Remember the minimum occupancy rule. Distinguish that B plus tree stores values only in leaves, making range queries big O of number of leaves, while B tree may need to visit internal nodes for each key. Key takeaway: B tree is the generalization of BST to many children, optimized for block storage. B plus tree further moves the data down to leaves for better sequential access. Explanation: we will build a B tree of order 4, so each node can have at most 4 children and at most 3 keys. The minimum number of keys per non-root node is the ceiling of 4 divided by 2 minus 1, which equals 1. Step 1. Insert 1. The tree is empty, so the root becomes a leaf with the K1. Step 2. Insert 2. The root leaf now holds 1, 2, and this is still less than or equal to 3 Ks. Step 3. Insert 3. The root leaf becomes 1, 2, 3, which is full but not overflowed. Step 4. Insert 4. Adding 4 would give 4 keys, causing an overflow. Split the leaf. The middle key is the second key, which is 2. The left leaf contains 1 and the right leaf contains 3 and 4. Create a new root with separator 2 and 2 child pointers. The tree now has a root with Ki2, a left child leaf containing 1 and a right child leaf containing 3 and 4. Step 5. Insert 5. 5 is greater than 2, so go to the right leaf containing 3 and 4. Insert 5, resulting in 3, 4, 5, which is still less than or equal to 3 keys. Step 6. Insert 6. The right leaf would become 3, 4, 5, 6, causing an overflow. Split the right leaf. The middle key is 4. The left part contains 3 and the right part contains 5 and 6. Push 4 up to the root. The root now has keys 2 and 4 with 3 children. The tree now has a root with keys 2 and 4 with 3 children. A left leaf containing 1, a middle leaf containing 3, and a right leaf containing 5 and 6. Step 7. Insert 7. 7 is greater than 4, so go to the leaf containing 5 and 6. Insert 7, resulting in 5, 6, 7. Step 8. Insert 8. The leaf containing 5, 6, 7 would overflow, so split at the middle key 6. The left leaf becomes 5 and the right leaf becomes 7 and 8. Push 6 into the root. The root currently has 2 keys and can accept a third, resulting in keys 2, 4, 6 with 4 children. The tree now has a root with keys 2, 4, 6, and 4 children. A leaf with 1, a leaf with 3, a leaf with 5, and a leaf with 7 and 8. Step 9. Insert 9. Go to the leaf containing 7 and 8, which becomes 7, 8, 9. Step 10. Insert 10. The leaf containing 7, 8, 9 overflows, so split at the middle key 8. The left leaf becomes 7 and the right leaf becomes 9 and 10. Push 8 up. The root already has 3 keys and is full, so inserting 8 causes the root to overflow. Split the root. The middle key is the second key 4. The new left internal node gets key 2. The new right internal node gets keys 6 and 8. The new root now has a single key 4 and 2 children. The final tree has a root with key 4, a left internal node with key 2 and 3 leaf children containing 1, 3, and 5, and a right internal node with keys 6 and 8 and 2 leaf children containing 7, and 9, and 10. All nodes satisfy the order 4 constraints, and the keys 1 through 10 are stored in sorted order. This step-by-step walk shows how splits propagate upward and how the height grows only when the root overflows. If you continue inserting 11 through 15, similar splits will occur, eventually giving a balanced B tree of height 2 with root 4 and 8 and appropriate leaves. Typical exam questions. What is the worst case height of a B tree that stores n keys and has order B? Answer: h less than or equal to the ceiling of log base B of n. State the minimum number of keys a non-root node must contain in a B tree of order B. Answer: the ceiling of B over 2 minus 1. During insertion, when do we split a node and what key is promoted? Split when a node would contain B keys. Promote the middle key, the ceiling of B over 2th key. Explain borrowing versus merging in deletion. Borrowing moves one key from a sibling that has more than the minimum, adjusting the separator in the parent. Merging combines 2 minimum filled siblings and pulls down the parent separator, possibly causing recursive underflow. Compare the search cost of a B tree and a binary search tree for 1 million keys if B equals 100. B tree height is approximately the ceiling of log base 100 of 1 million, which is 3. Binary search tree average height is approximately log base 2 of 1 million, about 20. Thus a B tree needs about 3 disk reads versus 20 pointer traversals. Common pitfalls. Confusing order with maximum keys. Order B limits children to B, not keys. Keys per node are less than or equal to B minus 1. Forgetting the root exception. the root may have fewer than the ceiling of B over two children, even a single leaf. Assuming every internal node stores data, in a B+ tree only leaves store records, internal nodes hold only separators. Miscalculating split point. The promoted key is the exact middle, the ceiling of B over 2th key, not simply the last key. Overlooking uniform leaf depth. After deletions, if you forget to merge up to the root, leaves could end up at different depths, breaking the invariant. Counting I/O incorrectly. The dominant cost is the number of node accesses, which is the height, not the work inside a node. Studying these points and practicing the insertion-deletion steps on small trees of order 3 or 4 will solidify your understanding and help you avoid the typical mistakes on exams.